Hello, this is Jack Jackson. Today we're going to be talking about the absolute value function, what it has to do with transformations, and what it has to do with solving equations. So, the absolute value of a real number is the distance that number is from 0 on a number line. So, you can actually think of this statement both forwards and backwards. The more primitive idea really is the idea of distance. So, if we start with the idea of distance, then we can define the absolute value as being the distance the number is from 0 on a number line. On the other hand, we could flip this around and do it in a more formal way, and we can define the absolute value of x as it is defined in this box here by this piecewise defined formula. Absolute value of x is defined to be x if x is greater than or equal to 0, and it's defined to be the opposite of x if x is negative. So, we can take that as a definition, and then the statement at the beginning, the absolute value of a real number is the distance that number is from 0 on a number line, then defines distance. But either way, whichever one you think coming first, it really doesn't matter. These two things give you the same concept. So, for example, the following graphic that you see here illustrates that both negative 4 and 4 are both at a distance of 4 from 0 on the number line. So then the absolute value of negative 4 is the same as the absolute value of 4, which is 4. Now, one thing you need to watch out about is some students find confusing when they see this negative sign in front of the x, or think of that as the opposite of x. But remember, which x's get sent to that part of this piecewise defined function? Only the x's that are negative, and then the opposite of a negative then is a positive. So even though you see this negative sign here, this negative x actually is not really a negative. It's the opposite of x, which x is negative, so the opposite of negative is positive. So this symbol, minus x, really is indicating a positive number. And so, of course, the top part, x is a positive number, or 0, so when it's all said and done, the absolute value of x is greater than or equal to 0 for all x real numbers. The distance between real numbers a and b on a number line is then the absolute value of b minus a. So, for example, to find the distance from 4 to negative 6, we can use the formula that there, absolute value of b minus a, and we go from 4 to negative 6. It's the final minus the initial, negative 6 minus 4, which is negative 10, then take the absolute value, and that becomes 10. And of course, you can just count the distance too, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so certainly that is a distance of 10. What does the graph look like? Well, for the part in the first quadrant, it looks like the formula y equals x, straight line. So it's a half of a straight line there, a ray, and includes a solid dot at the origin. The other part has an open dot at the origin, but it's filled in by the solid dot from the other part. And we take the opposite of x, y equals opposite of x, in the second quadrant. So this turns out to be two rays with a common endpoint here. You have a slope of negative 1 in the second quadrant, and a slope of positive 1 in the first quadrant. So actually, this turns out to be a right angle. That's what this one actually is. And of course, you can see what to do with it over here in the table. When you have a positive input, you leave it alone. The same input is output, same for 0. But when you have negative inputs, these guys have their negative removed, and it becomes positive. So the absolute value of some function g of x, if we apply that on the outside, so we're basically composing absolute value with another function, then notice what we have here. If we look at y equals absolute value of g of x, for the places where g of x, that is the y value on the original function g of x, are positive or 0, nothing happens to those points. Those points stay the same. But when g of x is a negative number, we do the opposite of that. So you've got y equals the opposite of g of x. Notice that's the same thing as negative y equals g of x. So what you're really doing is changing the sign on y. Now remember, we've done transformations, so we know that when we transform a relation by replacing y by minus y, what happens to the graph? Well, you change the sign on y in the table, and what you end up doing is you flip it over the x-axis. It's a reflection over the x-axis. So when you take the absolute value and put it on the outside of a function, and then you can think of that as a transformation that leaves the part of the graph that was above the x-axis or on the x-axis alone, but the part that was below the x-axis will be reflected over the x-axis. So you can think of that as the transformation of the original y equals x squared or y equals x, let's just look at that. So if you look at y equals x, we have a line that looks like this. But if we put the absolute value here around this x, then what it turns out to be is this part in the first quadrant is going to be left alone, but this part that's got a negative y's are going to be flipped. So can you see that as a flip over here from the third quadrant flipped up to the second, whereas the first quadrant was left alone. Now if we do this again for some other function, let's take, say, x squared minus 4, x squared, and then minus 4. Let's look at that example. Okay, and so notice part of this graph is above the x-axis and part below the x-axis. What's going to happen if I put absolute value on the outside of the whole thing? Well, that part that's above the x-axis, the part to the right of 2 and the part to the left of negative 2, gets left alone, but that part between negative 2 and 2, which was negative y, gets flipped over the axis. Let's do another example. Let's do x minus 2, x minus 3, x plus 1. And so we have a graph like this. What happens if we put absolute value on the outside of the whole thing? Well, notice what's going to happen. This part that's above the x-axis here between negative 1 and 2 is going to be left alone, and the part to the right of 3 is going to be left alone, but this part below the x-axis between 2 and 3 is going to flip up, and the part to the left of negative 1 is going to be flipped over the axis. Now notice when this happens, anytime the original function crossed the x-axis, when we take the absolute value on the outside of the whole thing, then we have, it has a tendency to introduce sharp corners here. Okay, so let me show you something else. I want to contrast this, just go back to y equals absolute value of x. I want to contrast this with something, let's say, like y equals x squared. Okay, in a way they're both similar. They're both decreasing in the second quadrant, increasing in the first quadrant. They both have origin symmetry. They both have a minimum here at the origin. But there's a significant difference here. When you zoom in close here, notice that this y equals x squared doesn't look like it's got any kind of a corner to it. It's kind of levels out. In fact, it almost looks like a horizontal line if you zoom in really, really close. But no matter how close we zoom in on this, that absolute value still has that sharp corner there. So that's a significant difference in the way those two things behave. So absolute values have a tendency to have a sharp change of direction when they're in the formula somewhere. Okay, going back to our PowerPoint, that's basically what this slide is showing you. Now let's try to apply absolute value in solving equations. Now, if you just got a constant and you're trying to find the absolute value, piece of cake. This is easy. You've been doing this since you were probably in elementary school. Absolute value of 8, 8. That's easy. Absolute value of 0, 0. Absolute value of negative 7, 7. So there's really nothing to it there. But when we start talking about absolute value when we have a variable, things get a little bit more complicated. Because if you've got an unknown variable, absolute value of x, there are two possibilities for most of the time. Because remember, when this function, when you graph it, it has a, let's just back up, here's the graph in red here on the left. Notice that basically for every y value, or at least every positive y value, there are two x's that give you the same y. So this is not a one-to-one function. In fact, mostly it's two x's going to the same y for the most part. And so we have to take into account both possibilities when we're trying to solve equations. So for any positive number c, there are 2 points, both negative c and c, which are distances c from 0 on the number line. So for any positive constant greater than 0, and you have absolute value of x equals that c, then either x equals negative c or x equals positive c. So, for example, if we have absolute value of x equals 4, then either x could be negative 4 or x could be 4. Notice the absolute value of negative 4 is 4, absolute value of 4 is 4. Those are both points that are 4 from 0 on the number line. So it gets a little bit more complicated because you have to take both points into account. So, again, if we have a positive function, positive c greater than 0, if we have the absolute value out of any expression that has x's in it, to call it g of x, then either that whatever's inside the absolute value has to equal negative c, or it could be positive c. So that's if you can get the absolute value by itself equal to a positive constant. So if we have the absolute value of x minus 5 equals 7, either the x minus 5 could be negative 7 or the x minus 5 could be positive 7. Or let's call g of x the x minus 5. So the g is 7 units from 0. In fact, I've graphed g in blue down here. Notice if you go 7 units to the right of 0 in this first graph, you get this blue dot here at 7. And if you go 7 units to the left, you get the blue dot at negative 7. So those are the two possibilities for g of x. Of course, we don't want to know what g of x is. We want to know what x is. So we have x minus 5 equals negative 7, or x minus 5 equals 7. Solve those two independently. In both cases, we add 5 to both sides of the equation. And so we get x equals negative 2, or we get x equals 12. And so now you can see that in the graph down here in red for the final answer. And we either get x equals negative 2, this single dot right here at negative 2, or x equals 12, a single dot right there on the number line. So, x is a distance of 7 units from 5. We can think of it that way. Remember, x minus 5 is the distance x is from 5. And notice I've lined my number lines up so that 5, the new center, is lined up with 0, the old center, and they're still 7 units away. And we just go 7 to the right of 5 and 7 to the left of 5 to find our values of x, negative 2 and 12. Okay, now let's do some inequalities. Well, notice the absolute value of x minus 2 equals 4 says either x minus 2 equals negative 4 or x minus 2 equals 4. Adding 2 to both sides of the equation in both cases gives us x equals negative 2 or x equals 6. And those are the two red dots here. Well, now, what we're saying here is the distance x is from 2 is 4. And that gives you exactly those two things. But what if I have the absolute value of x minus 2 is less than 4? We're saying the distance x is from 2 is small. The absolute value is small. That's a small distance. A small distance from where? From x to 2. How small a distance? Well, less than 4. So it has to be close to 2. How close? No more than 4 either way. So it has to be between, the x minus 2 has to be between the negative 4 and the 4, in which case that means x is between the negative 2 and the 6. So again, the boundary points there are the ones where absolute value of x minus 2 equals 4. And what we're wanting is the points in between, which are graphed in blue here, and that's the x's such that negative 2 is less than x, which is less than 6. On the other hand, if we do absolute value of x minus 2 is greater than 4, we're saying we have an absolute value that's a distance which is big. It's big. It's either way to the right or way to the left. How far? Well, more than 4 away. Okay? So if we call g x minus 2, g is more than 4 away from 0. So either 4 to the right or 4 to the left from 0. But that's for g. What about for x? Well, x in this case is really a distance from 2. So anyway, it's still a distance out to the right or out to the left. And the boundary point, again, is what we get when we put the equal to in place of the greater than. So again, our boundary points are negative 2 and 6. But this time we either go to the right of 6 or to the left of negative 2. And we could also do this with some test points. So notice if you test 0, you get 0 minus 2 is negative 2, absolute value of that is 2. 2, of course, is not equal to 4, so it's not a boundary point, but 2 is less than 4, so that'll be shaded in on the blue graph, but not on the green one. And similarly, you could test some of these others. 10 minus 2 is 8, absolute value of 8 is 8. 8 is greater than 4, so that's shaded for the green one, but not the blue one. And if you did something out here like negative 4 minus 2 is negative 6, absolute value is 6. 6 is greater than 4, so that's shaded on the green one, not the blue one. So if I'm going to do these three related equation and two related inequalities for 2x minus 8 and absolute value Oops, we have a typo there. I think that's supposed to be 6 all the way around. Yes, it is. Let's fix that real fast. This is supposed to be 6. And this is supposed to be 6. And while I'm in here, let me fix it. I think it's probably copied on the next slide. Okay, alright, back in business. Okay, so we have absolute value of 2x minus 8 equals 6, absolute value of 2x minus 8 is less than 6, and absolute value of 2x minus 8 is greater than 6. Well, the boundary points can be found by just solving the equation in red here. And this is just going to have two numbers, the two red dots on the graph. So we either have the thing we're taking the absolute value of, the 2x minus 8, is equal to negative 6, or the thing we're taking the absolute value of, the 2x minus 8, is equal to 6. So in both cases, we add 8 to both sides of the equation. We get 2x equals 2, which makes x equal 1. Or we get 2x equals 14, and that makes x equals 7. So 1 and 7 are the boundary points in red. Now, the less than is going to be sandwiched in between these, and the greater than is going to be on the outside of these. And you can see that in the graph and the test point. So we can also see this with a graphical method, a two-dimensional graphical method. We've solved equations and inequalities this way before. So if you let y1 be the left side, the absolute value of 2x minus 8, and by the way, absolute value is ABS on your TI calculator, and let y2 be the right side, which is 6, the places where these cross are going to be the points, are the places where the equation is true. And there are two of them. So you could do this on your calculator. I've done it here in Graphmatica, but you could do it on your calculator by graphing these two and then do a calc intersect for these points of intersection. Find the x value here is 1 and the x value over here is 7. So you bring those straight down. Those are the two red dots on here. When we're looking for absolute value less than 6, we're saying the absolute value, the red graph, is below the horizontal blue graph. Well, where does that happen? Well, it happens at this middle section between 1 and 7. Okay, if you're wanting absolute value then greater than 6, where does that happen? That's when the V shape there is above the horizontal line, and so that'll happen to the right of 7 and also to the left of 1. So remember what we've been talking about here though is when we have a positive constant. So if c is a positive number and we have absolute value of g of x equals c, then either g of x equals negative c or g of x equals c. If we have absolute value of g of x is less than c, then g of x is sandwiched between negative c and c. That is, negative c is less than g of x, which is less than c. And if we have absolute value of g of x greater than c, that says g of x is to the left of negative c or to the right of c. So g of x is less than negative c or g of x is greater than c. Now, what if we have a 0 or a negative constant there? Then things change a little bit. If c is 0, in other words, we have absolute value of g of x equals 0, there's really only one way that can happen, is for g of x to be equal to 0, however many times that happens. Because there's no, the opposite of 0 is still 0, so there's no plus or minus. If we say the absolute value of g of x is less than 0, that's never possible, because once we take the absolute value, it becomes positive or negative, not negative, positive or 0, but never negative. So that one has no solution. And when is the absolute value of g of x greater than 0? Well, it's not going to be true when g of x equals 0. It's not going to be true if g of x is undefined, but it'll be true for all other x's in the real numbers. So any x in the real numbers where g of x is defined and g of x is not 0, the absolute value of g of x will have to be greater than 0, because it can't be negative. Absolute value is always positive or 0. For a negative constant, g of x and an absolute value equals c has no solution, because the absolute value will never be negative. And the absolute value will never be less than a negative, because that makes it negative again. So no solution there. And g of x is greater than c is true for all real numbers, at least as long as g of x is defined. And so just use a little common sense on these last two when you have a negative on there, on the side there. So when you're solving these, get the absolute value by itself. Don't worry about what's inside yet. Get the absolute value by itself. And then this will tell you how to go about solving them. So after completing this this section and this video and related doing some homework problems, you should be able to do the following with and without technology. State the definitions of absolute value and distance between points on a number line, and distance from a point to the origin and between 2 points. We should be able to graph functions involving the use of absolute value by hand and with technology. And we should be able to describe the effect of composing absolute value with another function. In other words, take another function and then take the absolute value of the whole thing and think of that as a transformation. What does it do to the graph and the table and so forth? And we can also solve equations and inequalities involving absolute value. So that gives us an idea of absolute value. So being a piecewise defined function, it makes things a little more challenging when we get to equations and inequalities. Not terribly hard, but you do have to be a little careful because you have to take into account both possibilities.